So how we control the accuracy of the approximation? What will be the error bounds? Okay, well, the estimate of the error bounds of m sub n and nt sub n really depend on the second derivative. By the way, we don't address the estimate of the error in the in right-hand sum and left-hand sum, but turn out that the errors in the left-hand sum and right-hand sum depends on the first derivative. The error of the estimate of the error in the midpoint and the trapezoid depends on the second derivative. Let's write this statement. Okay, maybe that will be an extra challenge to prove this statement, to give a mathematical proof for this statement. Okay, but let's be practical. And what we're going to say is we're going to let, and you're going to ask me, what the heck am I writing here? I know that. We're going to say that let's have the absolute value of the second derivative. Let's bound it by some number k on the interval x goes from a to b, the closed interval ab. Okay? Remember, we are trying to estimate the definite integral from a to b. So, if you have a function f of x, so we need to know this function, and we know the second derivative, what we need to do, we need to look at the largest possible value of the second derivative on the interval. That's what this statement is. So k, so this is explanation, this is a note here, okay? K is the largest possible value actually k is greater than the largest. Let me write it again. It's Friday and my eraser is working overtime and it just ran out of eraser. So k is greater than the largest possible value of f double prime on the interval AB. Okay? So what is the error bound? Now, so let's say we establish this number k, and I'll show you an example before we depart so you see how this works out. And the error bound for the midpoint, the absolute value of the error bound, the error will be less than or equal to a number that generated by taking k multiplied by b minus a cubed divided by 24n squared. And the largest error when we do the trapezoidal approximation is bounded by k times b minus a cubed divided by 12n squared. One thing you can see from here that for the error when we do the midpoint has 24 in the denominator, or 24n squared, and the error and when we in the trapezoidal is 12n squared. you can see the factor of 1/2 in the errors. Also, you can see why when we double n, then we reduce the error, we decrease the error by a factor of 4 because of the square here. So let's wrap this up by giving you an example, okay? So in this example, we want to apply the error bound to example 1. So apply the error bounds to example 1. Okay, in example 1, remember we are looking at the integral from 1 to 2 of 1 over x dx. So the solution, okay? With n equals 5. Let's find the derivative. F of x equals 1 over x. So f prime of x will be negative 1 over x squared, right? Remember your differentiation. And f double prime of x will be positive 2 over x cubed. Again, this is x to the negative 1. This will be negative x to the negative 2. And this will be positive 2 x to the negative 3. Okay? So what is the possible value of 2 over x cubed on the interval x goes from 1 to 2? If x goes to 1, from 1 to 2, the largest possible value of f double prime will be obtained with the smallest possible value of x. Well, the smallest possible value of x is 1. So we're going to say that f double prime of x will be less than or equals 2. Okay? 2 over 1 cube. Therefore, we're going to choose, we'll choose k equals 2. Okay? Because 2 is the largest possible value of f greater or equal. So instead of greater, let's do this, greater or equal largest possible value, like so. So we have k equals 2, we have n equals 5, and now we are ready to calculate. Okay? What will be E sub m, the error as we evaluate the midpoint? Well, I'm looking here, the error should be less than or equal to k, which is 2, b minus a, which is 2 minus 1 cubed, divided by 24 times 5 squared. Well, that will be 2, 24 times 25. 4 times 25 is 100, so 24 times 25 is 600, or 1 over 300, or rounded to, actually not rounded, do it exactly, 0.003 repeated, like so. Okay? Now compare this to the error that we calculated earlier. The error that we calculated was 0.001, so it was well within 0.003 repeated. What about the error in the trapezoidal method? It's less than or equal. It should be exactly the same thing, except we divide by 12 n squared. So we'll have 2 divided by 12 times 35, which is 300. And twice as much will be 0.006 repeated. I think this is a wonderful place to stop. I'm sorry, early, 2 days in a row. Wow.